So here in day 8, this is just a quick review of the things that we've already discussed with the vector equation of a line, okay? And what we're talking about here, you got to understand here is that this vector equation of a line is really modeling the position of some object moving at a constant velocity, okay? It's constant velocity, that's what makes it straight, even in 3 dimensions. We had our vector equation, which this actually is in your formula booklet, but it's given as this. So you got to know what these parts are. R is our position, okay? A is our position at time 0, or our starting point. And by the way, if you notice down here, we have the same thing, just laid out for us a little bit more. Okay, so here's our starting point at time 0, plus t times our direction vector or velocity vector, vector b here. Or we could lay it out like this, ABC. Okay? And then from those, we have our parametric equations. One thing that might be helpful for you guys is to see this written with the notation that gave our vectors vertically. So x, y, z is x sub 0, y sub 0, z sub 0 plus t times ABC. And actually, guys, if you use our vector operations, you can come up with the component or the parametric pretty easily. Okay? We have t times a vector. Anytime you had a constant times a vector, you'd multiply each component by that constant. So AT, BT, and CT.
Wait, so the parentheses, is that vector, component vector form?
Yes. Remember, we can write our vectors either horizontally like this, and they kind of look like points, or we can use the angled brackets like this, horizontally, or we can use the IJK notation, which is really annoying, so don't ever do it unless you have to, or this vertical notation like this. And especially with the 3D vectors, this vertical notation can be helpful. All right. So as you see here, we multiplied t by that direction vector, and then if we do vector addition, we have x sub 0 plus at, y sub 0 plus bt, and z sub 0 plus ct. And that equals our x, y, z position. And you'll notice here, we could then directly take x equals x sub naught plus at. There's our parametric equation. And y equals y sub 0 plus bt. It's right here in the middle. And z is z sub 0 plus ct. Okay? So that's just a quick overview or a reminder of how we get those parametric equations. So I want to do a little bit of practice here, not just given 2 vectors, but one application is when we are given the equations of 2 different lines, okay? We always want to find, if you're asked for the angle between the lines, obviously when you have 2 intersecting lines, you're always going to have an acute angle or an obtuse angle, unless they happen to be perpendicular. But we will always give the acute angle as the angle between the 2 lines. Okay? So as we see this here, we have the formula that we looked at before. And it's the same formula, but here it's a matter of picking out the correct things to use as your U and V. Okay? So what would we use in this case as the u and the v?
You have to doesn't make it like you have to find the magnitude of the first equation by doing 12 times 2 or 12 times negative 2.
No.
Or you have to find the vector.
What vector are we going to use here?
You have to use each one. The one in the first equation and one in the second equation.
Okay, but the equation has two vectors in it. We have a position vector and we have a velocity vector, right?
Use the velocity vector.
Yes, that's the key. We've got to use the velocity vector from each one. And the velocity vector, remember, is always the vector that's being multiplied by your time. Okay? Notice I use t for time in the first and s for time in the second because they're not necessarily the same times. We didn't necessarily start the clock on both lines at the same moment. All right, so here what we're doing is we need to find negative 2, 3, 1 dotted with 1, negative 4, 5. Okay, so what does this equal?
So vector u is negative 2, 3, 1.
Yeah,
Okay.
we could call that vector u and we could call that vector v. All right, so how do we do the dot product? Do you remember?
Multiply them.
Multiply what?
2 by negative 2 by 1.
Negative 2 times 1 plus, good,
3 times negative 4
good,
plus 5 times 1.
good. All right, so we have a negative 2 minus 12 plus 5. Negative 14 plus 5 is a negative 9. Okay?
And then you have to add them up.
So now I know that the cosine of the angle between them is going to be negative 9 over the product of the magnitudes. Okay? So I've got to find the magnitude. So they're both going to be in radicals unless they come out perfectly. But let's do the magnitude of the negative 2, 3, 1. How do we do magnitude again?
The distance from, well,
Okay, it's from the distance formula. We already have the x1 minus x2, y1 minus y2, and so on in the components. So you're right. Square root of that negative 2 squared plus 3 squared plus 1 squared. So we have square root of 14. 4, 9, and 1. So there's that. Then we also need the magnitude of the 1, negative 4, and 5. Okay? So again, the square root of 1 squared plus a negative 4 squared plus 5 squared. 25 and 16 is 41. Plus 1 is 42. So we have the square root of 42. Which does simplify, but we're just throwing it in a formula anyways, so we'll just leave it like that.
oh, so
Okay.
if it's like that, we don't have to simplify the radical?
Yeah, we don't, I mean, it all goes back to what the point of the problem is. Here, the point of the problem is getting the angle, so,
Right.
okay? So, we plug that into our calculators, all right? So guys, go ahead and get out your calculators and let's figure this out. Okay, we get the negative 0.371 for cosine, and you take the inverse cosine. The fact that it's negative, we automatically then know that our angle that we're going to get is obtuse. And you got, what, 117?
111.
A 111?
Yeah.
Point
786.
786, all right, so let's do 111.8 degrees. Okay, now that is the obtuse angle, so how do we get the acute angle?
Subtract that from 180.
Subtract it from 180, yeah, so we will end up getting 68.2 degrees. And that'll be our final answer. Okay, so the second thing that we want to look at here is finding the intersection of two lines. Okay? Finding the intersection of two lines. And for this, we need the parametric equations of both of these lines. All right? Now notice here that S and T are two different parameters. One important thing is unless you are told that the times are the same, you can't just assume and use T for both. You need to use two different parameters here, because on the first line we may have started the clock now, and the second line we may start the clock now. You know, we might start the clock at different times. So as we look at line 1 and line 2, line 1, x equals what for our parametric equation?
-2 plus 3s.
Good, -2 plus 3s. And y equals, good, 1 plus 2s. All right? For line number 2, good. X equals 15 minus 4t, and y equals 5 plus t. Okay? Now, if these two lines are intersecting, for one thing, since I'm in 2 dimensions, I know they're going to intersect because my velocity vectors are different. Okay? All right, so if we're intersecting, that means these two lines are at the same value of x and the same value of y at the same time. Okay? So our x's have to be equal. So I'm going to take this -2 plus 3s and set it equal to 15 minus 4t. Now obviously I can't solve that equation right now because I have two different variables. Alright, but then I look at the second, I look at the y's, and I have 1 plus 2s equals 5 plus t. And now I have two equations with two variables, which you guys all know how to solve a system of equations. Alright? Now, you can simplify things a little bit if you want. If you want to get all the s's and t's on the same side and all the numbers on the other side, you can do that. We really don't have to, though.
So the equations are, well, the lines are equal to each other.
Yeah, basically you're setting the two lines equal to each other.
Assume that.
Well, we're assuming that because it says find where the two lines meet. If they're intersecting, they're going to have the same x and y coordinate at the intersection point. Okay? So what we would do in this case, I think the easiest way would probably be if I multiply this whole second equation by 4. Now why would I multiply this by 4? Yeah, I can get rid of the t's. Okay? So that's what I get when I multiply that. If I bring this equation down, I have a -2 plus 3s equals 15 minus 4t. And now I can combine those two equations just adding straight down. I'm adding the left side to the left side and the right side to the right side. So I have 2 plus 11s equals 35, and the t's cancel out. And now I have an equation that I can actually solve, and I get s equal to 3 if I subtract 2 and divide by 11. Okay? So now if I go back and I plug in s into my line 1, if I plug S into line 1, that's going to end up giving me the point negative 2 plus 3 times 3, and y equals 1 plus 2 times 3. So negative 2 plus 9 is 7, and 1 plus 6 is 7. So I have the point 77. Okay? We can double check by figuring out what t was. Alright, if I go back to one of my original equations and plug in 3 for s, let's say in that 1 plus 2s equals 5 plus t, I have 1 plus 6 equals 5 plus t, and that means t has to equal 2. Okay? Well, if t equals 2, and I plug that in, x is 15 minus 4 times 2, y is 5 plus 2, and I do get the point 77. So they do intersect there. Okay?
Wait. I was writing down and I got really confused. Where did you get the 2 plus 3 times 3?
The negative 2 times 3 plus 3? I took the s that I just found and I plugged it into my line 1. So negative 2 plus 3 times 3. There you go. Alright, so I know that they meet at 7, 7. Okay? Now, here's the thing. If this is two different objects moving, alright, we know their paths crossed at 7, 7, but one thing that we don't know is whether or not they actually met each other. Like, the two objects collided into each other. Well, but what could happen is the object that's on line 1 could have gone past 7, 7, and then a second later the object that was on line 2 may have passed through 7, 7. So they both hit the point 7, 7, but they may have done it at different times. Okay? Just like every one of you walked through the door, but you did it at different times. That's why we didn't have a pileup. Okay? Now, in this case, we really can't tell what's going on because we have two different parameters for our time. If we were doing a situation where we wanted to see if the two objects met, we would need to use the same parameter, and they would have to have the starting points happen at the same time. And that's typically something that we would end up being given. Okay? So here we have a case. We're going to assume that these starting points occur at the same moment. Alright, so I actually went back, and these are the same two lines that we said intersected at, I think it was 68.2 degrees. Okay, but here, since we're in 3 dimensions, we might have skew lines. It's not as obvious if the lines don't intersect as it is when there are 2 dimensions. If it's 2 dimensions, we have the vectors parallel, then they're never going to intersect. Here, it's not quite so obvious because we might also have skew lines. So what we have to do is kind of the same process that we just did. However, we need to check our answer, okay? So I'm going to start by writing the parametric equations for R. So for R, x is 12 minus 2t, y is a negative 15 plus 3t, and z is 15 plus t. Okay? Then we have for vector s, x is 3 plus s, y is 6 minus 4s, and z is 3 plus 5s. Okay? So then we combine all those and we are able to write 3 equations. Okay? Red and green kind of make brown, so we'll make our equations brown. Alright, so we have 12 minus 2t equals 3 plus s. We have negative 15 plus 3t equals 6 minus 4s. And we have 15 plus t equals 3 plus 5s. Okay? Now here's where the challenge comes in. Okay? It's a challenge, but in a sense it's not. Because at this point, in order to solve a system of equations with 2 variables, how many equations do we need? 2. Alright, we have 3, so we've got an extra. So what we're going to end up doing is just picking any 2 that we want. Alright, so I'm going to go ahead and pick these first 2. And I'm going to eliminate the s, because I can just multiply this whole first equation by 4, and then my s's will cancel out. Okay? So I'm going to multiply this one times 4, and I get 48 minus 8t equals 12 plus 4s. I have a negative 15 plus 3t equals 6 minus 4s. And now I can add straight down. My s's cancel out. I get an 18, and I get a 33 minus 5t. So I have a negative 15 equals a negative 5t, and that means t has to equal 3. Now, in this case, I do want to always figure out what s is. Okay? So, I had 12 minus 2t equals 3 plus s. So, 12 minus 2 times 3 equals 3 plus s. 12 minus 6 is 6, minus 3 is 3. Okay? So, here's what we have to do. We never used the z. All we've proven at this point is that these 2 lines, when their time is 3 on both of them in this case, will have the same x and y coordinate.
Wait, you only plug it into the first equation?
Huh?
You only plug it into the first equation?
Well, I plugged, you could plug it into all 3, okay?
You have to do all of
And
it.
eventually what we're going to do is we are going to figure out the point by plugging it in all 3. We don't have to do all this work again,
Third one?
okay?
Yeah.
What we're going to do for the z is, we know the x and the y should be the same. So if these 2 lines actually cross, then when we plug 3 in for t and when we plug 3 in for s, the z's should end up the same as well. Okay? So, I plug in 3 for t. Let me change colors here again. We'll go purple there. Okay? So if I plug in 3 for t, then that means I have 12 minus 6. So at t equals 3. 12 minus 6 is 6. 15 plus, negative 15 plus 9 is a negative 6. And 15 plus 3 is 18. So that's where line number 1 is at t equals 3. Okay? for line S, if S equals 3, then my point is 3 plus 3 is 6, and 6 minus 12 is negative 6. Now I knew those two were going to be the same. The key is this Z. 3 plus 5 times 3. 3 plus 15 does give me 18. So, do my lines actually cross?
Yeah.
Yes. All right? By the way, don't just show the work, make sure you answer the question. Do they actually cross? Yes. Do the two objects here meet each other? And the answer is yes, because,
Because the coordinates are the same.
well, they intersect, but how do I know not only do the lines cross paths, but the two objects that are on those lines hit each other?
Because they intersect when both the times are 3.
When both the times are 3, that's the case. And I told you, remember at the beginning I said the zeros occur at the same moment. All right, you'd have to know that in order to be able to say this, okay? So yes, the times are the same, okay? If line R got there at t equals 3 and line S got there at t equals 5, then they wouldn't actually hit each other.
Okay, so basically you just have to solve, or like, use the first two equations and then find t or s, and then make them equal to each other and find the other one. So then you have those two times and plug them in and make sure that they're the same number.
Yeah, yeah.